Okay, this screencast is to cover example 10.2.2 from the Orphanitis textbook. This example is a bandpass filter design using a Kaiser window. Alright, so we start with some frequency specifications. The sampling rate is 20 kilosamples per second. You have something that defines the first edge of the bandpass filter template. So you have an FSA, that's 3, an FPA of 4. Then you have the second edge where you have a pass band of 6 and a stop band of 8. We'll look at the filter template here in a second to show you what I mean by those. Alright, then you're also given the pass band ripple specification of 0.1 dB and the stop band attenuation of 80 dB. Okay, so let's look at the filter template, because you have to modify the Kaiser design just a little bit to handle a bandpass case. Alright, so here's what I was talking about. This is the bandpass template, so the bandpass response has to kind of trace within this region of white space here, and the gray space is not allowed. Okay, so the thing to notice is that there's two transition regions. There's an FSA, the edge of the first stop band. There's an FSB, the edge of the second stop band. All right, there's an FPA, the edge of the first passband frequency. There's an FPB, the edge of the second passband frequency. All right, what that gives you is two transition widths, delta FA and delta FB. All right, so as it's drawn here, you can see that delta FA is smaller than delta FB. So when you're modifying the Kaiser method, when you choose FA and FB in your design, okay, so that's the midpoint of the desired frequency response. You're going to need those in the desired frequency response. So when you choose those, you have to use the smallest delta F to make sure that you meet your specifications. All right, so what that means is that over here on this wider transition width, you're going to do better than specifications. That's not a problem to do better. All right. Okay, so let's go through it. Back to the problem statement. All right. I'll pass it. Hang on. Yes, here's the problem statement. All right, so I'm going to want you to do this for a problem that I give you. Put this into MATLAB. So you enter the sampling rate, you enter the stop band A, you enter the pass band A, you enter pass band B, you enter stop band B. All right, so you have the template entered into MATLAB. You give the ripple specification, you give the stop band attenuation specification, and from there you can calculate DFA, the first transition width, DFB, the second transition width, and then you just take the smallest, right? And your design will meet the spec if you use the smallest. All right. Then, as we did in class, you need to calculate the two deltas. You have, let me move this to the middle. You have delta pass with this formula. You have delta stop with this formula. That gives you two deltas. Again, the symmetry of a Kaiser method or Kaiser result means that you need to choose the smallest of those two. All right. Once you have the smallest delta, you can calculate the A value. This is the formula for alpha. I'm sorry, no, the A value is right. I got this in the wrong spot. Okay, sorry. All right. Once you have an A value, if your A value is bigger than 50, which it will be in this case, you can then calculate alpha using this formula. Right. The formula for alpha is in the book. Right. Then you use the formula for D. That's going to let you get your filter order. And from there, you read the Orphanitis book, and it tells you you can set FA and FB by just taking the passband edges and subtracting off delta over 2. or from the first edge, from the first passband edge. And then from the second passband edge, you add delta f over 2. Okay. So what this does is it gives you the exact passband specifications, and your stop band region is going to actually be a little wider, which is good. All right, you have a choice on that, but most people would choose this one. All right, from there, we can calculate omega A and omega B, which is what we need for our desired impulse response. Okay, so we just take FA and FB and calculate those as normalized frequencies in radians per sample. Okay. Next, we need to calculate the order of the filter. If you plug in, you'll get something that's not an integer, so that's why I'm calling it n and then n exact. All right, then I round up with this next line. All right, this piece of code is just to check to see if it's even or odd. All right, if it's odd, if it's even, you need to add 1 to it. All right, so that completes the Kaiser design process in terms of specifying n and alpha. What we need to do next is specify the exact impulse response. All right, so from there, what we do is we make a vector n that starts at 0 and goes up to n. All right, so that would actually be n plus 1 points long. Okay. All right, from there, we calculate the midpoint, because remember, the desired impulse response is non-causal and infinitely long. So what we have to do is window it to make it not infinitely long, to be finite, and then we have to shift it to make it causal. Right? So we talked about this in class. This is the formula for a desired bandpass response. Okay. So I just literally plug in the parameters that I've already calculated into this desired response for bandpass. I have to take care of the midpoint because at n equals m, remember MATLAB indices are off by 1, so that's why that says n plus 1. At n equal m, this would divide by 0, so I have to specify that case separately. All right. From there, I multiply the desired response by the Kaiser window. So this Kaiser window is built into MATLAB. Notice MATLAB returns a Kaiser window of length n, okay, when you read the help files, but our filter length is n plus 1, so that needs an n plus 1 there. All right. The other thing that you might want to notice is that I needed a prime to make the dimensions match between how we specified d and the Kaiser window function. Okay, so the last thing I want you to do is plot the frequency response for both the Kaiser methodology, a rectangular window, and a Hamming window. All right, so this is code that lets you do that. All right, it turns out freq_z lets you specify an output. Okay, so when you give it an output, you can get the frequency response, which would just be a series of complex numbers at each frequency value. So I'm going to call that W, meaning omega. Okay, so when you give it an output, all right, we're given an FS here, so it will give you a frequency variable here, okay, and an output variable here. All right, what we want to do is plot all these at the same time. Okay, so notice the first one, I used B. That was the Kaiser design. The next one, I used D. Okay, so we can put some comments here. This is the Kaiser. All right, without the window function, this is the rectangular window. Some people call it the implicit window because you don't really have to multiply by a window. Okay, and then the last one is the Hamming window. And what I did for the Hamming window is just took the desired response and multiplied by a Hamming window of length n plus 1. Okay. So after that, I have things ready to go in a plot. So all I'm doing here is plotting the magnitude response. Remember H1, these are complex numbers, so you need to take the magnitude and then I put it on the dB scale. All right, I added in an x-axis label and a y-axis label. All right, so when I hit run, we can check out some of the answers here. Okay, so when I hit run, you'll see here's the frequency response. Let me drag the MATLAB window over. We can look at N's 103, which matches the example in your book. Alpha is 7.8573, which also matches example 10.2.2 in your book. Okay, so I'd like you to do something similar. I'm going to give you a slightly different set of input parameters, and you just go through the same process using MATLAB.